Hello. Today I'll be going to present my seminar topic on microarchitecture for function as a service. My name is Shomik Dotto and I have been guided by Professor Vishwabandhan Panda on this topic. So this will be more or less 30 minutes journey where first we will try to understand FaaS microarchitectural challenges, then mitigation strategies for those challenges. Finally, we will explore how we can run FaaS efficiently on general purpose CPUs. And this is going to be the overall flow of my presentation, where we will start with understanding FaaS architecture. Then we will try to identify FaaS bottlenecks, that is challenges. Then we will give the mitigation challenge strategies for those overcoming those challenges. And finally, how to optimize FaaS to run efficiently on general purpose CPUs. And throughout this whole journey, in between, we will take help from a background paper while doing all the performance analysis. So let's start with the first paper, that is architectural implication of function as a service computing, which came in Micro 2019. So let's start with answering the question, what is FaaS? So we will try to understand it from two perspectives. One is the customers of FaaS, that is developers, and another is the providers of FaaS platform, that is the cloud providers. So let's try to see the developer's perspective first. Let's say a developer wants to build an application like this. When on an image upload event, this triggers a cloud function, which in turn creates process that image, create a thumbnails, save the image into a database, and parallelly upload the thumbnail of that image to some shareable storage so that other in the internet can see and download the image. For that, he will go directly to the Google Cloud Run platform, that is a FaaS platform provided by Google itself. There he will first have to select which runtime or which language you want to code. He can code then and there directly. The code should be in a form of a small function. Then he has to select how much memory he want to allocate to his function. Then which trigger points or entry point to his function, and deploy. That's it. That function will be live on internet, as is easy as this. So from this we can get the idea that why is this called a serverless model, because from developers perspective, developer can build and run application without managing their own server infrastructures like hardware, OS, software packages. This is a pay for what you use model, that is developer has to pay for only the CPU time and the memory their application is actually running, not for the idle time of their application. And this drives the developers to create short-lived and compact function to minimize the cost. And according to the Datadog 2023 survey, more than 50% of all cloud customers, including AWS, Google Cloud, Azure, uses serverless nowadays. So this gives the idea how much serverless is important nowadays. So let's see from the cloud provider's perspective, though the names is called serverless, but it's actually not serverless because cloud providers has to maintain all these servers, hardware, OS, software packages. Let's understand the serverless model with comparing it with the earlier or conventional model. In this image left hand side, we can see these bare metal virtual machine containers are actually conventional model where the resources got occupied constantly in server. In contrast, for serverless model, as developers are writing the code only and the rest of the stack, that is app container, language runtime, operating system, hardware, are being maintained by cloud providers only. So when the functions are ideal, cloud providers can dynamically revoke those resources to free the server space. So this is the actually the comparison between conventional and serverless model. So let's see some characteristics of serverless applications. So actually, a serverless application generally are organized as a graph of tiny stateless function, like it's shown in this image. And these densely packed functions on a server often interleave. And from the image, right hand side image, we can see the interarrival time between two invocation, that is from the first invocation of this function to the next invocation of the same function, is observed to be quite high. Uh, so next, moving to the next paper on this, that is lukewarm serverless function characterization and optimization. We will from this through this paper we will try to understand the FaaS bottlenecks it came into in ISCA 2022. So let's first define state the problem statement of my seminar, that is lukewarm invocation. So what is lukewarm? The word lukewarm means moderately warm. Let's understand it with cold invocation versus warm invocation versus lukewarm invocation. So this is the typical memory hierarchy of any modern CPUs. So in case of the first invocation of a function, when it's demands for a instruction on memory, it gets missed in every stage of the memory. So this is called cold invocation. In case of back-to-back invocation of a same function, it gets hit in the all the part of memory hierarchy, because all those cache states, BPU states are preserved in CPU memory hierarchy. In contrast, when function interleaves, that is in between reinvocation of the same function, other functions come and run in the same CPU core, then what happens when the function, let's say here f1, interleaves and gets reinvoked after a while, then it gets its states preserved in main memory, because main memory size is quite high, but the microarchitectural state inside the microarchitectural structures of CPU inside CPU, like L1, L2 cache, L3 cache, branch predictor unit, all got thrashed by the in-between functions. So this phenomena is called lukewarm invocation. So what's the problem here? Because FaaS functions are generally short-lived, this overhead that again reinitiating these states into the memory hierarchy, this time cannot be amortized. So let's see the performance implication of lukewarm invocation. So from this graph, authors have plotted for different workloads, the CPI for back-to-back versus interleaved execution. So here we can see for interleaved execution, CPI got increased by more or less 70%. So to analyze this issue further, we will take help from the background paper of ISPAS 2014, a top-down method for performance analysis and counter architecture. Let's see it. So according to this paper, CPU cycle can be categorized in this 4 broad category, like fetch bound, which consists of instruction cache and instruction TLB bound CPU cycles. Second is bad speculation, that is branch target buffer and conditional branch predictor bound CPU cycles. Third is retiring. Retiring are the good CPU cycles, we can say, because those are the cycles for which the instructions are getting committed. Another is the backend bound, which consists of the memory hierarchy bound CPU cycles and execution unit bound, like ALU unit bound CPU cycles. So the fetch bound and bad speculation bound consists typically together called front end of pipeline, and memory bound and execution bound typically called the back end of pipeline. So this top-down hierarchical approach has been adopted by tools like vTune and Linux Perps. and is gonna be used for further performance analysis in the upcoming papers. So let's see now, segregate the CPI, cycles per instruction, according this to the top-down CPI analysis. So here we can see, for the interleaved execution, the whichever the additional stall cycles we can find for the interleaved execution, then back-to-back execution, 56% of those stalls are due to fetch bound cycle. So this gives us with the idea that instruction fetch is a critical performance bottleneck for interleaved execution. So before going to give a mitigation approach for handling this challenge of instruction fetch stalls, we first have to understand the instruction footprint of FaaS workloads. So for that, the authors have run each FaaS workloads multiple times, and they have calculated the Zaccard index of the multiple runs of the same FaaS workload, and where the Zaccard index signifies in 0 signifies nothing in common, and 1 means exactly common. So they have performed this experiment for the instruction footprint of each FaaS workload. So here 0 means nothing in instruction footprint in common in multiple run of the same function, and 1 means exactly the instruction footprint matches for the multiple runs of the same function. From this graph, we can see most of the workloads are tends to 1 only. That, and more than 85% of cache blocks are same in repeated invocation of the same function. So from this we can take away that instruction footprint is almost same across invocation of the same function in case of FaaS workload. So with this idea, when we try to address the instruction fetch bottleneck, the first idea comes into our mind is that can we exploit this high commonality to improve performance? The answer is yes, we can with jukebox. It's an instruction prefetcher. So this records instruction working set of one invocation and replace those recorded instruction working set on the reinvocation of the same function. The idea here is to exploit the high commonality of functions of when reinvocating the same FaaS function. So let's see the record phase and jukebox record and replay phase. When a function gets invoked, the OS first schedules it into CPU. For as the function is coming for the first time, it gets missed in the whole memory hierarchy. The data gets fetched from main memory. Here at sitting at L1 I cache, the jukebox recorder detects the L2 misses depending upon the time L2 is taking to fetch the data. And with that, it records the L2 misses into a first in first out virtual address buffer. When the buffer gets full, it evicts their entry into a dedicated region in main memory. In the case of replay, when OS senses the reinvocation of the same function, it triggers the dedicated region to fetch the metadata into a prefetch engine, which first converts the virtual to physical address conversion, and it warms up the ITLB also, and it prefetches into L2 cache, so that when the function actually demands from memory hierarchy, it gets a hit from L2 cache. So let's see the performance improvement by this approach. So here authors have plotted the speed up of jukebox with normalized baseline, where baseline is all microarchitectural states flushed out. So here we can clearly see from the graph that jukebox improved interleaved execution speed by 18% on average. And the reason because obviously that 85% L3 instruction misses are mitigated. And jukebox only takes 32 KB per function main memory metadata overhead. So this is the overall picture of the jukebox approach. So now let's move to the third paper, that is another mitigating approach, advanced mitigating approach, that is called warming up a cold front end with Ignite. It came in Micro 2023. So here author first tried to analyze the performance of the state of the art prefetchers like jukebox, as we discussed right now, with the ideal case. Here ideal case means perfect L1I ITLB BPU where nothing is getting flushed out. And here boomerang also is there. Boomerang is another prefetching approach that we can just talk about. And here from the graph we can see that there is a ample amount of space for improvement for the prior work. That state of the art front end prefetchers fall well short of the ideal case. Now to analyze this speed of degradation, we have to again take help from the background paper of FaaS. Here the earlier prefetch approach, the jukebox, talked about this part of the front end of the pipeline, that fetch bound pipe part. Now this Ignite is gonna focus on this whole front end pipeline, that is fetch bound, including BPU, branch predictor unit bound CPU cycle. So to progress on that, let's analyze this branch predictor unit with the top-down CPI approach. So for that, authors have plotted the speed up they have got for the state-of-the-art boomerang plus jukebox. Then they have kept BTB warm, that is branch target buffer. They didn't flush it out. Then on top of that, they again kept CBP, that is branch predictor, conditional branch predictor warm. So this both two together, BTB and CBP, creates the branch predictor unit. And they have compared with that perfect, that is the ideal case. So here we can see cold with warm BPU unit, branch predictor unit, we are getting more speed up than the state of the art prefetcher. So from here we can take away that cold branch predictor unit state arises from in case of lukewarm invocation, and this leads to a poor performance for lukewarm invocation. So to address this cold BPU state, the idea comes in mind again is that can we explore the high commonality to make BPU warm and improve the performance? So the answer is yes, Ignite. It bulk restores the working set. It records the BTB insertion of one invocation and replace the BTB working set on reinvocation of the function to restore instruction, branch targets, branch direction. The idea or the insight behind this that BTB working set, branch target buffer working set, provides a complete and non-redundant control flow graph representing the whole program. So let's see the record phase of Ignite. The record this unit introduced in this Ignite approach. It records, monitor the BTB insertions and records it, stores it in a dedicated main memory region. Now, while replaying, when the function gets invoked, it replaces the metadata, reads the metadata trace sequentially, and it replaces it into the branch predictor unit and the memory hierarchy parallelly. So it inserts it into the branch predictor unit, the branch target buffer, and bimodal branch predictor, and it also prefetches from main memory to L2 cache. So whenever the function gets reinvoked, it gets hit in a L2 cache. Also, the branch predictor unit is also pre-trained. Let's see the improvement achieved by this approach. So from the graph, again for different workloads, they have compared the prior work speed up with the Ignite and idle case speed up. So Ignite has achieved 43% on average speed up over next line prefetcher. And we can see also it has significant more speed up than the state of the art prefetcher. And this is due to Ignite covers 67% of the initial branch misprediction that happened due to the cold branch predictor unit, which Ignites have omitted or mitigated. But just a disclaimer that Ignite only talks about the front end of pipeline. The back end stalls also still needs to be analyzed further. So this is the whole picture of the Ignite. Now let's move on to the last paper of today's presentation. This came in Micro 2024. This is called Mosaic, harnessing the microarchitectural resources of server in serverless environment. So this talks about a little different idea, is that how we can mitigate, how we can perform FaaS workloads efficiently on general purpose CPU, not a special FaaS CPU. So let's understand the challenges for this. Is that general purpose CPUs is about few powerful cores which are best suitable for running monolithic application. So for serverless workloads, we need many smaller cores, and this needs a specialized CPU. But from cloud providers perspective, maintaining different server types increases the cost. So the goal of this paper is to improve performance of FaaS workloads on general purpose CPUs. So this will be the outline of the paper. We will first analyze the serverless workloads on general purpose CPU. Then we will introduce the idea, Mosaic CPU and Mosaic scheduler. Then we will evaluate the idea. Let's start with analyzing the serverless workloads on general purpose CPU. For that, here authors have plotted the execution time of a particular FaaS workloads while decreasing L2 and LLC cache size gradually. From here we can see they have decreased LLC size, LLC per slice size from 1.88 MB to 0.13 MB, and similarly L2 size from 2 MB to 0.13 MB. But from the graph we can see, due to that much reduction in L2 and LLC slice also, the execution time effect is very minimum. That is, reducing an L2 and LLC slice sizes has minimal effect on serverless functions. Similarly, for branch predictor unit also we can see the hit rate decreases negligible for until we go to 1/32th size of the branch predictor unit. So from this we can take away that serverless functions can still run efficiently with small hardware resources. So to address this problem of bigger resources, that the question comes is, can we cut resource and power waste in serverless by rethinking this large hardware state? And the answer is yes. By Mosaic, it partitions the hardware into chunks. So what Mosaic do? Mosaic has a two-part. Mosaic CPU slices the big hardwares into small chunks, which are combined into tiles. And Mosaic scheduler predicts this tile's optimal tile size to be assigned to a particular function and schedules the function to a particular Mosaic CPU. And the idea behind this is that to dynamically assign resources to a function with smaller chunks on an on-demand basis. So let's see the Mosaic CPU and Mosaic scheduler approaches. No, so the overall architecture of the Mosaic is like that. This is a SaaS platform, and this is the cloud server running in the cloud provider's end. When a function fx gets scheduled, so it has two parts: ways the software part and the hardware part. So when fx gets scheduled, the scheduler consults with the profiler first to get the optimal tile size and which CPU core to schedule, and then based upon that it schedules on the Mosaic CPUs. So now let's focus on first Mosaic CPUs. Let's say this is a core 1 to core n we have here. So if we focus on a particular core, let's say here core 1, here all the inside core architecture like microarchitectures structures like L2 cache, L2 TLB, branch predictor unit, branch target buffer, LLC, everything are partitioned into small chunks. And if we focus on a particular L2 cache here we can see the whole L2 cache are partitioned into chunk 0 to chunk 7. Now for a particular function, let's say in core 1, function B is scheduled. So function B will be having some number of child chunks, that is chunk 1, chunk 3, chunk 4 here. And this mapping for a function to a chunk is maintained in another hardware table that is called state table. Similarly, for Mosaic CPU, a scheduler, when a function gets invoked or invoked into the system, then first scheduler gets the optimal tile size in a pre-profiled from a pre-profiled database, and it reads the state tables of each of the Mosaic CPUs and decides in which core to schedule this function. Here, as function X was already prior running in that this core, left hand side core, scheduler will prefer first tries to schedule in that core only to reuse the chunks. So this is the overall idea. Now let's evaluate the Mosaic approach. Here authors have plotted the average latency of different workloads, FaaS workloads, and with respect to baseline is the conventional server without any hardware partitioning, and baseline plus affinity here is that same function is getting re-invoked a number of time in a same CPU. So we can see for Mosaic, the latency, average latency is reduces by 59% on average. And similarly, from the power consumption point of view, we can see from the graph that now power has been for in Mosaic implementation, the power has been reduced by 22% on average. So in general purpose CPU, Mosaic improves the throughput by 25% while using less power. So this is the overall picture of the Mosaic approach. So we started with understanding the FaaS microarchitectures in the first paper. Then in the lukewarm paper, we identified the FaaS challenges and bottlenecks. We have stated the problem statement. Then we started to come up with some solution for the problem statements like jukebox. Then our advanced solution or mitigating approach, that is Ignite. And finally, we talked about a different problem statement. So to how to run FaaS efficiently on a general purpose CPU to decrease the cost at cloud providers and in between we took help from this top-down performance analysis time to time. So this was all from my today's presentation. Thank you all. Q&A, yes, you can type in a comment section. Thank you.